All right. So now we're going to be doing two different types of problems. Two different totally types of problems that they could have when you are having trees and you're trying to solve them. So what do I want to do first? I think I want to show you actually the second part, because technically this is just an extension of the factoring problems that we previously did. Now, if you guys remember in Algebra 2, if ever we asked you to find solutions or to solve a quadratic polynomial, what would you do first to solve? Right, that's what you do first, always. What method are you doing? Starts with an F and we just did it. Factor. Yes, thank you. So if ever they want you to solve, first you factor, and then you take each factor and you set it equal to 0, right? And then variable all by itself. That's what you can do to factor, or to solve. You first factor, and then set equal to 0, and solve. Well, these three types of problems, these three examples, are actually even easier. Instead, well, the last one isn't. The last one will actually have to factor, but I'm just going to do number one. Instead of just factoring, whenever we are missing the b value, what can we do instead? You could factor the 2, but then, I mean, you could, like, but I'm trying to get you to see an even easier way. We have, if, maybe it'll make it easier on the see it. If we had this, what could we do to solve this? It's not completely square. It's easier than completely square. We wouldn't divide by 2 because then we would be putting a divide by 2 on the x. Okay, okay, we move the negative 2 over and then what? What do we do to get the x by itself? Oh my gosh, we can square root. We can square root, right? And then we would get x equals or minus the square root of 2. Same exact concept here. We add the 2 over. Now there is more stuff. We add the 2 over, and then what do we have to do? First, well, so this becomes cosine squared of x is equal to 1/2. And then what? How do you get the variable unsquared? Square root. Yes. Uh-oh. There we go. So we have now the square root of cosine squared of x is just cosine of x. Now, if we were trying to solve this like normal, from here, if we were trying to find here's an angle, I would tell you look on your unit circle and figure out now cosine is always our x value, right? So find out which angle has the square root of 1 over 1 is the x value. Would you be able to find this on the unit circle? Square root of 1 over 2. No, it's not on there. Because this technically be simplified. Whenever you are square rooting a fraction, Another way to write it as is the square root of the numerator over the square root of the denominator. And then what is the square root of 1? 1, but remember, whenever you actually square root something, it's not only the positive version, it's also the negative. So right now we have plus or minus 1 over the square root of 2. Would you find that as the x value on your unit circle? Would you say that again? Ah, exactly. You cannot have square the denominator. So you have to rationalize the denominator. I mean, this is going to pop up a million times where you have to rationalize the denominator. So hopefully you're figuring this out. Anytime you have a square root in the denominator, you multiply by the square root over the square root, and it becomes, in this case, square root of 2 over 2. Now, can you find that on your unit circle? Oh, yeah. Oh, for sure. One of the most used values on your unit circle. So tell me, where in the unit circle do I have an x value that is either positive square root of 2 or negative square root of 2? What angles have that x value? Yes, I'm going to go in order though, but you're totally right. Those two have the positive square root of 2 over 2. What about the negative square root of 2 over 2 as the x value? Ah, that's 3 pi over 4. What else? Mm-hmm. I see how you guys are loving to say give an degree and gradient. What else? Thank you. Because most times your math Excel and every higher level math course is going to want your angles and radians. All right. So this type of problem is where you have specific solutions that make your statement true, right? We're trying to find out when or for which angles does 4 times the cosine squared of x minus 2 equal 0. We're finding specific a specific set of solutions, specific solutions, versus what we're about to do. Okay, now here comes the big part of today. You are going to have this last page of your notes handy. Not quite yet, but in a second. They're asking us to simplify the expression using identities and properties of multiplication. So this is the very first time that you guys are seeing a trig identity of a problem. So instead of like asking you questions, I am just going to show you me solving. Okay. Maybe at the end, at the very end, I'll ask you a question, but I'll show you what I will do to simplify this. The first thing you have to do is notice that on the right hand side, you have two terms. And on the left hand side, you're multiplying binomials. They're totally different formats here. So the first thing I want to do is try to get everything to just be single terms, meaning I'm going to multiply my binomials there. So here I'm actually double distributing just like I did earlier. Ooh, where was I going on that? Just like I did earlier. So I have 1 times 1, which is 1. Then I have 1 times negative 3 sine x, which is negative 3 sine x. Then I have 3 sine x times 1, which is 3 sine x. And then 3 sine x times negative 3 sine x becomes a negative 9 sine squared x, because I'm multiplying sine of x and sine of x. And you get sine squared. And then I'll just copy down the right hand side. I'm not doing anything to it. I need to combine my like terms. So here, my plain sine x's can be combined together. -3 plus 3 cancel. And I'm left with 1 minus 9 sine squared of x. Now what I'm going to do is I'm going to try to get like terms together on each side of this equation. So right now I have a constant 1 on the left-hand side. I also have a constant of -8 on the right-hand side. So I'm going to try to bring them together. I'm also going to try to bring the x values together as well. Even though they're different functions, sine and cosine, I'm going to try to put them together because I know that there is something called trigonometric identities now that I can use to help me simplify equations. So here I'm going to add a, and I'm going to add 9 sine squared of x. So these will cancel. I'm left with 9 is equal to 9 sine squared of x plus 9 sine squared of x. So I can't really, right? These are not the same variables. Sine and cosine are not the same. That's why I didn't try to get everything to one side, because I know I can't factor this. It's the same as if you had 9 equals 9 times x plus 9 times y. How are you going to factor that, right? So I now need to think, okay, how can we simplify? What notice on the right-hand side that I can do these values to make it a little bit simpler? Yes, Dario. Dario said yeah, which is exactly right. I can pull 9, which pull out, divide out, whichever. 9 sine squared of x plus cosine squared of x. So now I know I can factor it, and I right now have sine squared of x plus cosine of x with no numbers. I don't have any numbers with my sine and cosine. So what I do to try to see if there's another way I can simplify this is I take a look at my trigonometric identity. Is there somewhere on the paper where it has a cosine, I'm sorry, a sine squared of x plus a cosine squared of x? X being a variable, meaning you can replace it with theta. Morris already, yes. I mean, kind of. He put the squares in the wrong spot, but we'll forgive him. Take a look at the Pythagorean identity. It says sine squared of theta plus cosine squared of theta is equal to 1. That means that this whole thing, whenever I'm adding a sine squared function plus a cosine squared function of the same variable, it can be replaced with 1. This whole thing can be replaced with 1. So this becomes 9 equal, oh, I should do in blue. 9 equals 9 times, now the whole thing is replaced with 1. So in this, 9 equals 9. So notice that what we actually did is not solve. We didn't solve for a certain solution. What we did was prove. We proved using trig identities that one side of this equation is equal to another. Meaning, as long as we are inputting x, inputting a certain variable, any number into this equation, the left-hand side will equal the right-hand side. This is an algebraic using trig identity. So that's what it's trying to go over here. That's what it's asking. You need to do for, I believe I asked you on the Excel for these definitions. So first is the conditional equation, which is like the first example I went over. The conditional equation, let me get this, is an equation that is true only for certain input values versus an identity, which is the second type of problem, is an equation that is true for all input values. It's actually just a much more complex version of this. If I had the equation 2x plus 3 equals 2x plus 3, I could input any x value I wanted. The solution set for this is all real numbers. It's all numbers. Versus the solution set for this is only specific values. And the one we went over, those solutions 504, 3, 5, 5, 4, 7, 5. Versus on this one, we could input anything. We could input anything. I hope that clarification makes sense. So honestly, most of these problems that I'm about to go over on the back of this, oh, come on, scroll. Oh my gosh. Oh my gosh. Are just a much more complex version of having the exact same thing, the exact same side of equation equal to, um, it's so we're not going to remove it all. What did I want to 3, 4. Oh, okay. So I'm going to have time to go over two of these. Two of these, and I will record myself doing the rest. I will record myself doing the rest. So what I'm actually going to do here is I'm going to pause this recording.